welcome back to the fifth class, which is we are going to continue with our journey about different electrode conformation. So we'll talk about electrode conformations. So, in the last class I told you the first conformation we talked about is intracellular. So where your electrode is inside versus outside and you are measuring the voltage, the current across it, mostly the voltage. Okay. So basically you are doing a current clamp measurements. The next was I told you that we will talk about a patch clamp conformation. Patch clamp conformation was needed for a very different reason, because if you look at this picture, whenever you are inserting an electrode, there is a lot of leakage and there are a lot of problems. The cell will die fast. So one of the things which was the modification which was done is where if this is the surface of the cell, you bring an electrode like this. It's a glass electrode filled with extracellular fluid or intracellular fluid, depending on what kind of conformation you are using. So this is the recording electrode RE. Okay. Now you bring it closer. So I'll only highlight, I'll kind of magnify this part. Okay. What exactly is happening on the membrane? You give it a gentle suction and you get that membrane inside. And this is what was the major work of Neher and Bert Sackman. And then eventually what will happen, you break the seal and this membrane becomes almost part of the electrode like this. Or you can even pull out this membrane itself to study its properties. Okay. Now, if this inside is filled with intracellular fluid IF, then it becomes a continuous thing. And there you can really inject current inside the cells very easily. You can change the voltage or you can vary the voltage and you can study it. This particular discovery, though I am unable to go in further details of it at this stage, because this is not really part of it, but I will go as much as I can. This conformation was the breakthrough, what we considered as the patch clamp. Why it is a patch clamp? You are clamping, means you are holding. So here holding a part of the membrane, patch of the membrane. Okay, clamping patch of the membrane. At this stage, you have an axis. If this is the membrane, say for example, this is the area under your electrode. So that means you have a direct access to those tons of ion channels which are present there. And at times, people, what they do, they fill this electrode with extracellular fluid and they pull this membrane, and what you see a conformation something like this. The tip you see and there are a lot of these, and you dip it in a intracellular fluid, assuming, so you have only the part of the membrane here and you have the extracellular fluid here, and you dip it in an intracellular fluid. So these are not realizing that they have detached from the cell, and yet you can at the molecular level in a real time. Why this technique is so very powerful is that you see the movement of things across a protein, across a membrane in real time. When I say real time means when we do techniques like X-ray crystallography, cryo determination, cryomicroscopy, all these are moments you are freezing the moment. It's a snapshot. Unlike electrophysiology, electrical sensors, where you are getting a real time movement of ions, movement of molecules across the membrane. Such thing never happens in any other technique, and that's why people love these kind of techniques where they could read out the motion, or they could read out those nanoampere current, picoampere current, femtoampere current across some of the most tiniest machine evolved in nature. That's why these techniques are so profoundly powerful and real time. So, you could have this kind of conformation like that, or you could become part of the cell as I showed you in the previous conformation, and you can vary the voltage. You can have those wonderful voltage pulses across the membrane, positive voltage, negative voltage. You can inject current and you can see the voltage, vice versa. You can hold the voltage, you can measure the current. The sky is the limit, and that's why some of these techniques, so voltage clamp, you can use it for current clamp, but mostly it was used for the voltage clamp. And not only that, this was used for a whole range of ion channels studies. This further gives rise to a different form of study, which in the same line called, so say for example, here you are, so what we are going to talk about is this particular technique. What is a planar patch clamp? So, we talked about the intracellular recording, we talked about the patch clamp recording. Before I move to any of those, I will talk about the planar patch clamp recording. What is planar patch clamp? So, yeah, let us use this slide. So, say for example, when we are talking about moving an electrode, and I am not going into the whole instrumentation of it, and okay, let me at least add one more thing. This whole patch clamp discovery or recording of electrophysiological recording really got a boost in 1960s. Now, you have to see how it got a boost. 1940s and 50s saw a big revolution in the world of electronics, because this is the time when these three people, Barden, Britton and Shockley, they are all from Bell Labs at that time, erstwhile Bell Labs, it is no more existing. They discovered crystalline silicon and its semiconductor properties, and this completely altered the world of microelectronics. So much so, some of the powerful amplifiers were developed, which could pick up signals of an extremely low current range. Lot of very good electrometers were discovered at that time or developed because of the development of crystalline silicon as a device material. So, this is the era of microelectronics, and of course, for Barden, Britton, Shockley won a Nobel Prize for this discovery, and thereafter one of them went ahead to get the second Nobel Prize for the theory of semiconductor. But where biosensor field got influenced is the whole microelectronics change the perspective of the people who are working on biosensing, at how much lower current you can measure. And it is exactly at that time, it was Ireniher and Bert Sackman, they were all working on these kind of well developed amplifiers. And it is a very, how I put it, some of the best people who developed these amplifiers went unnoticed. They never got the best of the best awards in the world, but those are the people who developed those amplifiers which changed the landscape of biosensing completely. So, 1960s, 70s is when lot of electronics entered the biological world for recording and other purpose, and what we saw is one of the biggest rich harvest was the patch clamp technology, which uses some of the powerful amplifier from Heka and other amplifier builders. Okay. So, now coming back. So, when we are talking about these patch clamp technique, so we are talking about picking up. So, you have the cells sitting on a dish and you are kind of pulling a part of the membrane and studying. But in 1990s and it is a pretty tedious process, they try to develop a very new technique. What they said, instead of creating a hole like this, if we have a surface where cells are growing, but cells are growing over nanopores. There you have the nanopores. These are small holes, and interestingly underneath they have these electrodes which are sitting there. So that the kind of recording what you are doing, you do not need to do any manual labor, you just have to give pulses, and these pulses will break these membranes and they will create a patch setup which is planar. So, the cells are sitting, you are not approaching it from the top, you are rather approaching it from the bottom, they are already set. So, cells are growing on top of the electrodes which are embedded or which are made on top of a surface. On that surface you are growing the cells, something like this. These are the cells. So, now what is happening, you can approach one cell with multiple electrode at one time, which is also feasible, but it is pretty tedious process, and you can control the surface in such a way that you can get extraordinarily good recordings from it. And this discovery is slowly, though it is not very popular yet, but in the world of high throughput screening, HTS, high throughput screening of drugs and toxins, this technology is gaining tremendous popularity in last 2 decades. If I remember right, that I saw a first evidence of this planar patch clamp array that was in San Diego in I think the year was 2001, 2002, either one of them, when there is a neuroscience congress which held, and I was there, and I was very fortunate to see this technology, and it was really wonderful to see that how you can cut down on the timing of the recordings of these kind of things. Since that I have been following it, it is common in industry, but there are issues with it. Of course, it is not that simple the way I am drawing it on these computer screen, but that is another development which has happened simultaneously. So, basically when we are talking about patch clamp, we are talking about the advantage what it garnered is called the voltage clamp. You can have this. Why these currents were essential? You might wonder, because if you go back, you realize I was telling you about these kind of toxins, say for example 4-AP, aminopyridine, curare, TTX. Okay. So, most of these toxins are not broad scale, these toxins are specific. They bind to sodium channels, they may bind to only part of the sodium channel, they can bind to potassium channels, or they can bind to only a part of the potassium channel, they can reduce the sodium current a bit. So, these toxins, especially most of these bioterrorist agents, are extremely, either they are purely invasive, they will just destroy the whole membrane, there you can't do anything, but many of the more sophisticated ones attacks or target specific part of sodium channel, they will slowly weaken the body, and you will not even realize that they are doing it. So, that is why it was very important that we have a direct access in terms of voltage clamp, so that we can study the ionic current, or which is also called the current generated across the ion channels. These ion channels are in the range of angstroms. So, you realize that these are extremely smallest machines humanity the privilege to see today. We are living in a beautiful time where we could see some of these at least close enough, at least maybe at 3.5 angstrom, we could see the architecture of these machines, how they have developed, because some of these machines hold potential to filter seawater. If you have something which only allows sodium to pass, you think of it, if you could emulate such channels, such structures, we could completely change the way how we are suffering from water problem, because there is a lot of water across the earth. We have to purify it. Ocean, the biggest source, how you purify it. So, while we are talking about bioterrorism, there is a counter aspect, peace. So, in order to understand, you see how all these things are converging at one point, how we are slowly realizing, wow. Similarly, there are these toxins like curare. There are several other toxins which are being used in several parts in the several tribes. They target neuromuscular junction. So, in other words, they are targeting the nerve to muscle transmission of electrical impulse. Because there is one more thing which I did not add, I just wanted to add. It slipped out from my mind while I was talking to you about what are the different excitable cells of the body. There is one more which I did not mention. So, now since I am talking about it, now I will take the opportunity to neurons, and these are the other ones, skeletal muscle and smooth muscle. These are also excitable cells. Not only these are excitable, these are also mechanically active. Okay? These are not only excitable, they are mechanically active cells, because they have a contraction coupling apparatus with them. They contract, your hands move, your heart beats. They are in a way electromechanical device, which most of the engineers call as MEMS, micro electromechanical systems. These are the nature's nano electromechanical systems, NEMS. This is how nature has evolved. Today, we are trying to having a top down approach to understand them, but the nature has already evolved these NEMS, MEMS, all these acronyms which are across the whole board of mechanical and microelectronics and material science, even in biology. The fact is, nature already had things like far below NEMS, nano electromechanical system, and these are the classic examples of cardiomyocytes, skeletal muscle, cardiac pacemaker cells, smooth muscles. Smooth muscles, which is the muscles which are allowing your food to travel through the gut. They all are some of the finest machines we are talking about. Now, while I am telling you that why this is important is because when we understand the kind of current, then we can understand the resolution of every toxin, how it is acting, and that is where the whole cell biosensor field becomes so very beautiful that you could sense. So, you can use them for insecticides, you can use them for pesticides. There are the opportunities and the, how to put it, the possibilities are enormous, extremely enormous. Out of the world, there are enormous possibilities which are there. So, from here, as I have already mentioned you about the planar patch clamp, we will, from the next class, we will move to the one which I have enumerated earlier. So, from here we will move on to the extracellular conformations, microelectrode arrays, and then the real beautiful stuff, which is not popular though, is silicon electronics merging with biological neurons, the world of field effect transistors, solid state electronics with electrochemical weight electronics. The marriage of these two, which is the FET, which is the frontier where you can take down electronics, unlike ionic motions, which are far more bulkier. You can make recordings, but this is extremely noisy, and this is still not very popular. Again, the venue where it got really its first breakthrough is Germany. So, if you look at much of these technologies, they all originated from Germany, and there are lot more to understand, lot more to explore. So, in the next class, we will move on to field effect transistors. First of all, we will have to extracellular conformation, how the recording looks like. Then we will move to microelectrode arrays, MEAs. Very famously, they call it, in short, they call it MEAs or planar MEAs, because it's in planar MEAs, and then we will move to field effect transistors. So, I will close the class here and looking forward to share the rest of the journey with different developments in biosensing, in the world of biosensors and toxins, and how they are shaping our counter research against bioterrorism. Thank you.